Dear learners, you're welcome back for this second session. I remain Odoi Henry, your physics teacher today from Namugongo Secondary and Vocational School. In our last lesson, we looked at gravitation, and we said that gravitation refers to the force of attraction between two masses in the universe. We're also able to state Kepler's laws of gravitation and then Newton's laws of gravitation. We said Kepler's laws has law 1, law 2, and law 3. Where law 1, we say that it states that planets revolve around orbit around the sun in elliptical orbit as a point of focus. Then law 2 states that the imaginary line joining the planet and the sun sweeps out equal area at equal time interval. And then law 3 states that the square of the period of revolution of the planet about the sun is directly proportional to the cube of the mean distance from the sun to the planet. And then Newton's laws of gravitation states that the force of attraction between two bodies in the universe is directly proportional to the product of their masses and inversely proportional to the square of their mean distance apart. We were also able to derive the dimension of the universal gravitational constant G, and we stated its units. Now, this time around, in this second lesson that we have started, we are going to look at how to use Newton's third law of gravitation to verify Kepler's third law of motion. Kepler's third law of motion, of gravitation, not motion. Kepler's third law of gravitation, we say that it states that the square of the period of revolution of the planet around the sun is directly proportional to the cube of the mean distance between the planet and the sun. So this is what we are going to verify. And like I've said, we can verify this using Newton's laws of gravitation. We are going to consider the planet of mass MP moving around the sun. If this is the sun, I'll write it here. If this is the sun of mass ms, and we also have the planet of mass mp. The planet is somewhere here, of mass mp moving around the sun. We have two forces which will act on these two bodies. Number one, we shall have the force of attraction between the sun and the planet, and also we shall have the force which will keep this planet to move around the sun. That force is called the centripetal force, and we shall also have the force of attraction F. That one shall get it from Newton's laws of gravitation. Let us look at the first one, the centripetal force. Centripetal force. How can we get the centripetal force? We know very well from Newton's second law of motion. Force is given by mass times acceleration. This is mass, this is force, which we call the centripetal force. And then this acceleration, since the planet is moving in a circular path around the sun, we shall call it the centripetal acceleration. Now, mass we know it, but we need to get an expression for acceleration. We know that acceleration is given by change in velocity over change in time. Then we need first of all to get an expression for velocity. We know that velocity can be defined as the rate of change of displacement or distance. Let me write distance, but it's displacement divided by what? Divided by time. For us to get this, we shall consider a body this planet here, when it is displaced from this point A to say point B, at that point B, at that point, when the angle here, okay, displaced through this angle, can call it a very small angle, delta theta. In time, delta t, also very small time. The distance moved by the planet from point A to point B is given by this arc. We can call it S. And we know that velocity is the distance out of time. This arc is just a part of the distance of this circular path moved by the planet. We know that when the planet moves from this point round, from here round up this point, it will have covered a total distance called circumference. And that distance is given by 2 pi r. Then also, so that distance is circumference 2 pi r. But now it has moved only from here up to this point, meaning it has covered just part of the distance through that angle. So that distance, therefore, will be given by delta theta out of 360 degrees times the total distance, which is 2 pi r. Now, divided by the total time, we can say delta t. 2 pi is 360 because pi is 180. So 2 pi is 360. Meaning this one and this one can cancel. Then we shall get velocity equals to delta theta divided by delta t times r. Delta theta out of delta t, delta theta over delta t is angular velocity denoted by that symbol omega. Therefore, velocity in this case can be expressed as delta theta out of delta t, which is omega times r, where r is the distance between the planet and the sun. R is here, this distance. Okay. After knowing the expression for velocity, we have V equals to omega r. We can therefore get the centripetal acceleration. Centripetal acceleration. Centripetal acceleration can be defined as the rate of change of velocity with the time for a body moving in a circular path. Rate of change of velocity with the time for a body moving in a circular path. So we shall have A equals to rate of change of velocity. Now we shall also get change in velocity. Change in velocity, we shall consider this body. When it moves from point A to point B, its velocity will change. We shall say that at this point, it has this, moving with that velocity, and even when it reaches here, it will still have the same velocity v. Now, we can resolve this velocity v into its components. This angle will still remain theta, which is here. So, vertically we shall have v cosine theta, and then horizontally we shall have v sine theta. Then also we shall get change in velocity parallel to this line. Can call this one OA, and then perpendicular to line OA. Parallel to line OA, we shall have v sine theta minus 0. And then perpendicular to line OA, we shall have v cosine theta minus v. But for small angles in radian, v cosine theta is, for small angles in radian, cosine theta is approximately equals to 1, and then sine theta is approximately equals to equals to theta. Therefore, we shall say that the velocity, the change in velocity here, will be given by the component of velocity which is perpendicular, which is parallel to OA. That is this one here. Because this is 1, 1, we shall get here 0, but this one will give us V theta, since this one is in theta. Therefore, we shall say that change in velocity will be V theta divided by time, t. And our expression for V is omega r. So we shall have omega r times again theta divided by time. Where this one here, it is also omega, angular velocity, the rate of change of the angle of revolution for a body moving in a circular path. So A will be omega squared, because this one is omega r. That is our centripetal acceleration. Now, after getting an expression for centripetal acceleration, we can therefore say that centripetal force F is given by now M, and then A, which is omega squared r. This mass is the mass of the planet, and then r is the radius of orbit of the planet around the sun. After getting this, that is one force. Then we shall also say that from Newton's laws of gravitation, we also have F equals to G, mass of the planet, mass of the sun, divided by r squared, where r is the distance between the planet and the sun. For a planet revolving around the sun in orbit or elliptical orbit, the centripetal force is provided by the gravitational force. Therefore, these two forces has to balance. We shall have mp omega squared r being equals to g mp ms all over r squared. You will see that mp and mp will cancel, so we shall have omega squared r being equals to g ms all over r squared, where ms is the mass of the sun. But omega, we have said that it is the rate of change of the angle of revolution for a body moving in a circular path. So we shall have omega being equal to theta all over t. This angle is 360 degrees if we consider the planet moving around, and then the total time taken is the period, which we can still call it capital T. 360 degrees in radians, it is given by 2 pi. So omega will be 2 pi divided by t. And this will therefore be given, B equals to this will therefore be equals to 2 pi out of t squared times r being equals to g ms out of r squared. When we open the bracket here, we shall get 4 pi squared out of g squared r equals to g ms all over r squared. When we cross multiply, we shall get t squared g ms being equals to 4 pi squared r cubed. Then t squared will therefore be equals to 4 pi squared out of g ms times r should. When you look at this, you will find out that this one, 4 pi squared over GMS, they are all constants. So this one is a constant, leaving us with T squared being directly proportional to R cubed, which verifies Newton's third law, which verifies Kepler's third law of gravitation, which states that the square of the period of revolution of the planet about the sun is directly proportional to the cube of the distance between the planet and the sun. We are also going to look at how to derive the mass of the sun. And for us to come up with that, we shall consider the earth revolving around the sun. The earth revolving around the sun. So we are looking at mass of the sun, mass of the sun, mass of the sun. For us to get the mass of the sun, we shall consider the motion of the earth around the sun in an orbit of radius 1.5 times 10 or 11 meters. So if this is the sun and this is the earth, so I have the earth of mass MOE, this is the sun of mass MS. Still we shall also have the force of attraction between the earth and the sun. Then we shall also have the force which keeps the earth to move around the sun, and that force is called the centripetal force. So we shall have centripetal force given by F equals to ME omega squared R. This ME is the mass of the sun, this is angular velocity, and then R is the radius of orbit of the earth round the sun. We have looked at how to come up with this centripetal force. Now, we shall also have the second force, which we shall get it from Newton's laws of gravitation, where we have F equals to G ms me all over R squared, where ms is the mass of the sun, me mass of the earth, this is the universal gravitational constant, this is the radius of orbit of the earth around the sun, and that is the force. Now, these two forces has to balance for the earth moving around the sun. The centripetal force is provided by this gravitational force. So we can call this one equation 1, we call this one equation 2, and we shall say that equation 1 equals to equation 2. Me omega squared R equals to G ms me all over R squared. Now, to get the mass of the sun, we just make ms the subject. First of all, me will cancel, and we shall remain with omega squared R equals to G ms all over R squared. Ms in this case will be equals to omega squared R cubed divided by G. Divided by G. Now, omega, we also say that it is the rate of change of the angle of revolution for a body moving in a circular path. And we have seen that omega is given by 2 pi all over t. That one we have derived it. Now we shall put it here. We shall say ms, mass of the sun, equals to 2 pi all over capital T squared times R cubed divided by G. This will give us ms equals to 4 pi squared R cubed all over T squared G, like that. Now what is remaining is just to substitute the values of this. This radius of orbit of the earth around the sun, We have said that is given by 1.5 times 10 power 11 meters. Then also universal gravitational constant G is 6.67 Newton meter, 6.67 times 10 power negative 11 Newton meter squared per kilogram squared. We are going to substitute those values here. Ms will be equals to 4 times pi is 22 out of 7. We square it. Times r, which in this case is 1.5 times 10 power 11 meters. This one is cubed. Divided by g, which is 6.67 times 10 power negative 11 times now the time. The time which the earth takes to revolve round the sun is equivalent to 1 year. And 1 year has 365 days. So we shall convert that one to time in seconds. Shall have 365 days times 24 hours in 1 day times 60 minutes in 1 hour times 60 seconds in 1 minute. When we compute this using our calculator, remember we have t being squared, so this one will be squared. Using our calculator, an estimated value of ms, which is the mass of the sun, is 2.0 times 10 power 30 kilograms. That is the mass of the sun. So this is just a constant. Whenever they want you to use this in the question, this constant will be given to you. More so on the first page of the question paper. They will tell you mass of the sun equals this. Universal gravitational constant G equals this. So don't mind of these values here. They are constants and they will be given to you. Like we have started by using Newton's laws of motion to verify Kepler's third law, using Newton's laws of gravitation to verify Kepler's third law of gravitation or planetary motion. We considered the motion of planet around the sun in orbit, and we balanced the two forces which do act between the two bodies. That is the force of attraction between the two bodies, and then the centripetal force which enables the planet to move around the sun. Then we came up with the calculations until we verified Kepler's third law of gravitation. I'm again reminding you, you should be able to state Kepler's laws of planetary motion, all of them, law 1, law 2, and law 3. You should also be able to state Newton's laws of gravitation. You should be able to derive the dimensions of the universal gravitational constant and stating its units, and you should be able to use Newton's laws of gravitation to verify Kepler's third law of gravitation, and you should be also able to come up with this value for the mass of the sun. I would like to end here for today. Thank you so much for listening. We shall meet again next time. Thank you so much. May God